Looking at our second notebook now. And once again, it's called molecule manipulation. And so we have more screen real estate. I'm gonna hide those folders again. And what we're going to do in this notebook is we're using a library called RDKit. RDKit is for chem informatics. And so the goal of this notebook is to take one of the ligands we downloaded in the previous notebook, 13U. We're going to chemically modify that using RDKit. And so the first question is, how can I load files using RDKit? We're going to answer that in just a couple of cells. And then how can I manipulate and create new molecules from an existing molecule? That's the process of the rest of this notebook. So the objectives are to understand the utility of the different Python libraries utilized in the notebook. I actually skipped the second one. We ended up not using smile strings here. And then we're going to modify the ligand file in a meaningful way and test the stereochemistry or electrochemistry and to save that modified file for future use. Now, we start this notebook with an ideal structure. Why are we doing that? This is the ideal structure we loaded from the PDB. Well, that's a structure that's already been optimized. And so that's a really good starting point for us to go as we go forward. The process of manipulating ligands, changing them, manipulating proteins in the docking process, it's not plug and play. It's a very subtle thing. Changes can happen. And so we'll be operating in that space. And the libraries we'll be using here, once again, we'll be using RDKit, the Chem Informatics Toolkit, and then 4 different subsets of RDKit. Chem, once again, this is for molecule manipulation, so we'll use this to change atomic numbers and things like that. IPython console enables us to control the image quality for the chemical structures. Draw is a part of RDKit that enables us to do chemical drawing. And AllChem is a subset of RDKit that enables us to optimize structures in 3D. All right, so in our first coding cell, we're going to import the libraries we need to start. So we're going to, from RDKit, we're going to import chem. From rdkit.chem.draw, we're going to import IPython console. And from rdkit.chem, we're going to import draw. You might ask, well, you've already imported chem from RDKit. Why do you need to import draw from rdkit.chem? A couple things. A lot of this depends on how the library is structured. But another thing is, if we import draw from rdkit.chem, later on we can just use draw as a reference to the drawing library. We won't have to have rdkit.chem.draw to use it. All right, so the next 3 commands are just to configure the display. And IPython console is a library that does display things. And the first thing we're going to do is we're going to set ourselves up to use SVG graphics. And quite honestly, I've forgotten what SVG stands for. Just looked it up. It's called Scalable Vector Graphics. So this is going to give us high quality images. No matter how we do. Maybe you remember bitmaps, maybe you don't, but bitmaps tend to be grainier. The next thing we're going to do is we're going to have IPython console set one of the draw options so that add atom indices is an option. That means that the index for each of the atoms in a structure will appear. This will enable us to do some manipulations. And then the size of our structures is shown here, 600 by 600. Sets the size of the image. So we're going to start off here. We're going to download this ligand from our ligands folder. And if I open up that folder for a minute, ligands, and I scan down there a little bit, I can see that 13u_ideal.mol2 is right there. So we're in good shape. It's there. We can pull it. So I hit this command, and we now have that mol2 file in the variable called ligand. Now we're going to modify this ligand. Oh, and when I type in ligand, it actually shows the picture. So here's our ligand. We have a 6-membered aromatic ring here, a guanidino group on the end, peptide bond here, a 5-membered ring, there's actually an 8-membered ring here. It's hard to see in the way it's presented. So there are a number of ways you can modify things in RDKit. I would guess the elegant way would be to create some subgroups and then combine those, okay? We're not going to do that. We're actually going to just change things one atom at a time, which is why we have this add atom indices option. So we'll know which atom we want to change. All right, so in this first cell, we're going to, we've already got our 13U ideal ligand. We're going to modify that. We'll call it mod ligand N. And so that's a new variable we're declaring. And we're actually going to load the 13U ideal structure in that ligand, or in that mod ligand N variable initially. But then what we're going to do in the next line of code is we're actually going to get the atom index for 23. If we go back to the previous picture, 23 is this position right here. Okay, it's on the 6-membered ring, aromatic ring. So we're going to get that, and then we're going to set the atom index to 7. Or I'm sorry, the atomic number to 7. All right, so that changes a carbon to a nitrogen. So if I hit Shift Enter here, then here's my ring with a nitrogen at that position. But we got a little problem. The little problem is that the nitrogen has 4 ligands to it. And so this is not an aromatic ring. We need to fix that. So it's still that nitrogen is now at position 23. So we're going to define an atom and say mod ligand N at atom index 23. That's our variable atom now. So we're going to say atom dot set num explicit H's. So we're setting the number of explicit hydrogens at that position. We're going to say that's 0. All right. And now in the next cell, we're just going to hit Shift Enter to run that cell and see if we fixed it. And we did. Now, one of the issues for me as I'm going through this notebook is sometimes I won't run a cell that I need later. So it's important to be careful to make sure you run all the cells that you need. All right, so we've created the modified version with a nitrogen in the aromatic ring in place of a carbon. The next thing I'm going to do is actually do a methyl derivative of that molecule. But in order to see that, I want to see the hydrogens because I'm going to replace a hydrogen with a carbon. So what I'm going to do in this first command is we're declaring a new variable, mod ligand methyl, and using the chem library and the mol from mol2 file function to take that original ligand that we have. So we're just downloading the original ligand again. And I'm going to say remove HS equals false. So the default is that it will remove them. We're going to say it equals to false. All right. And so what's going to happen then is that the hydrogens will appear. So if I look up here, here is our original ligand, 13U, and we have hydrogens here. And this is the carbon number 23 we changed last time to a nitrogen. We're back now, it's a carbon in the original structure, but I'm going to modify this hydrogen to make it a carbon. All right. And so that's position 59. So I come down here and it's not 62. I'm going to replace that with a 59. So once again, we're defining a specific atom. I'm going to say atom equals mod ligand methyl, which is this structure, dot get atom with IDX, with index 59. So that's that position. And now we say to that variable atom dot set atom num 6. So we're going to change it from a hydrogen to a carbon. And then atom dot set num explicit HS. So this is going to give us explicit hydrogens in that position. I'm going to tell it 3. All right. And the next command here, mod ligand methyl equals chem. And check to make sure I get the syntax on this statement correct. And I'm going to say remove all HS. Now, it's interesting because in this command, each of the words starts with a capital letter, or in this function name. But if we look up here under remove H is equal false, that's not a capital letter. That's, to me, that's it's just funny that they're not consistent that way. Anyway, so we've done that, and I'm going to enter that. And so here we're showing our original ligand with a methyl group at this position. If you're not used to looking at organic chemistry stick structures, the straight line coming out here means that this line ends in a carbon and that carbon has 3 hydrogens attached. It's implied. All right, so now we're actually going to take these molecules and optimize them. And in order to do that, we need the all-chem portion of RDKit.chem. All right, so that's, I guess I'd call it a sub-library. And so the first thing we're going to do is to take that original mod ligand N, which we made before with the nitrogen substituted in the ring. Take a look at it here. Yeah, this one right here. So what we're going to do is we're going to add all the hydrogens to this, and then we're going to use the optimize function. All right, so we're calling it mod ligand NH because it has the hydrogens attached now. And we're telling that chem sublibrary of RDKit to add hydrogens to mod ligand N. All right. Now, the next part of this is we're doing a constrained embedding. What that means is that we're going to keep the ligand molecule in the same position. We're just moving around the hydrogens to make sure that they're sterically correct. Okay, so they're in the right position with respect to each other. And so that's what a constrained embed means. And you can learn more about it if you follow this link. So the heavy atoms, which is the carbons, the nitrogens, the oxygens, those positions are not going to change. The positions that will change will be the hydrogens. So I just ran that, and here is our mod ligand NH. So it's got all the hydrogens in the proper positions. All right. The next thing we're going to do is use the all-chem sublibrary of RDKit.chem to optimize this molecule. And MMFF here stands for Merck Molecular Force Field. So this is a set of force fields that were determined for the purpose of predicting structures or docking processes. All right, so we're going to optimize this molecule. And that was fairly quick. And now the structure has changed slightly from what we saw a couple panes ago. Now our next step here is to complete this process on the methyl ligand. And so we have, now we call it mod ligand methyl H. So we're going to put hydrogens on this. So we once again use the chem sublibrary of RDKit .add HS. And we're going to add that to that mod ligand methyl molecule we had before. And we're going to again do a constrained embed. Now, constrained mole, that's our variable we declared. That's not a reserved word at all. But constrained embed is a function in the all-chem library. And so it takes, actually, this is the target. This is what's going to happen. This is what we're feeding it in this process. So we do the constrained mole here again. And this gets us, notice our carbon at position, it's now numbered position 30 for some reason. Anyway, this is the carbon, the hydrogen we changed to a carbon and put 3 hydrogens on it. And there it is, which is 3 with its 3 hydrogens attached. And then we're going to go through and do the same thing we did before with the MMFF optimized molecule conf. And it went through and did all those calculations. And what we need to do now is we need to save all of these new structures. I'm going to open this directory again. All right, so here's our original directory. And notice we're going to be making a folder called ligands to dock. So watch for that to appear. And then we need to have another variable called ligand H. Now, ligand H is actually our original molecule, 13U, all right? But in this case, we're going to leave the hydrogens on. We're not taking the hydrogens away. So remove HS equals false. So that's going to do that with ligand. And then subsequently, what we're going to do is we're going to write 3 files to that folder ligands to dock. So I'm going to hit the execute button and watch in this window for ligands. Oh, ligands to dock is already there. All right. Well, anyway, I executed that. And the number 11 shows up, which means it's complete. If I open ligands to doc, there are our 3 files that we use in the future. Now, we have an exercise, and the exercise for this notebook is to take a different ligand from the ligands folder, and to define that as a ligand you wish to work with. Basically take this command we used before, but we're going to have a different 3 characters here. All right. And we want to use the commands from this notebook to identify one hydrogen you would like to change to a hydroxyl group and then make the change. So I would encourage you to pause the video at this point for about, 10 minutes or so, as long as it takes you to do this, and then to come back and do it. So what I'm going to do is first, I'm actually going to take the text from this window, copy it, and paste it in here. But what I'm going to do now, instead of using ligand 13, I'm going to use ligand 32. So it's going to be 32U. I'm going to call it ligand 2, once again, to distinguish it from previous ones. And maybe I'll call it ligand 32. That way we'll know what it is. Then I'm going to look at it, see what we've got. All right, so this is a molecule not too different from 13U, but instead of having an 8-membered cyclooctane ring here, we've got a 6-membered aromatic ring here. All right, so we have a ligand, and so the challenge here is to identify a hydrogen we'd like to change and change that to a hydroxyl group. And so what I'm going to do then is I'm going to declare a variable mod ligand OH equals, and I'm going to use a command we used in an earlier cell, CHEM, so that's calling the chem sublibrary of RDKit dot mol from mol2 file. And so that's a function in chem. Open parentheses. I'm going to say ligands /32U ideal mol2. Close the quote. Oh, not yet. I'm going to say remove HS equals false. And notice that false is also bold and changed color. It's a reserved word. And now I'm going to take a look at that ligand to see what I can see. So now at this point, we call it mod ligand OH, but we haven't changed it yet. It's still identical to what's up here. But now we're going to see it with hydrogens attached. Oh, 32U. I think there's an underscore here. There we go. All right, so I made an error there. I didn't put the underscore in, and so it didn't find it. Not surprising. So here's our structure. All right, and looking at the structure, I'm going to pick this hydrogen to replace. So this will give us a phenolic hydroxyl on this ring, and I'm picking this hydrogen pretty much on a whim. But if I look at the structure, it's far enough away from other things that it can go in there and probably won't disrupt the structure when we go to optimize it. All right. So we're going to change position 55. So I'm going to go back and use a command we used before. We say atom equals mod ligand underscore OH and get atom with index, it's IDX 55. So I've selected this position. The next thing I'm going to do is I'm going to say atom set atomic num, open the parentheses, 8. So that's going to change the hydrogen to an oxygen. And then I'm going to say atom dot set num explicit HS So we now attach one hydrogen to the oxygen to get an OH group. And let's take a look now at our molecule. And there it is with an OH group at that position. But notice it's also showing all the hydrogens. So just for interest's sake, let's go through and remove those hydrogens. So I'm just going to say mod ligand OH equals chem dot remove all HS mod ligand OH. So this removes all of the hydrogens. You're going to see it removes all of them except one. So we go mod ligand OH again. And it's kept that actually the hydrogens are still there on the nitrogen here and here and here and here, and on the oxygen that we changed. So that's the end of the exercise and the end of our work with the second notebook. And now you have the materials you need for the third notebook.